So Tracy Young is an engineering manager within the government services at Schweitzer Engineering Labs. Mr. Young joined SEL in 2012 and has worked within the government services division ever since then. He is a retired Marine Corps captain, and his last command had him serving as project manager, contract officer, rep, and presidential communications site lead within the White House Communications Agency. He received his BSCS from University of Utah and an MS in Information Technology Management from the Naval Postgraduate School in 2009. Mr. Young has experience in performing database development, data mining, SCADA protocols, and software development. And he is currently leading several research teams on communications and cybersecurity related projects. So I will leave the SCADA honeypot analysis, turn that over to Tracy.
Hi, good afternoon, and thanks. Again, my name is Tracy Young. I get the pleasure of talking to you about a project that we got to do a few years ago. This is that SCADA honeypot, and we're going to go over some of the development that we did with that, and then a bunch of lessons learned at the very end there. So a bunch of the different things that we're going through, where we started at with that research, some definitions, some previous attempts that were out there, what my initial plan was for that infrastructure and how we were going to get that together, the different stages that we were going through with that development, what were the baby steps that we were trying to take at the beginning, looking a little bit at the application structure, what we were trying to connect and how and why, give credit where credit's due. There was a lot of open source libraries that we were looking at to either use or to use as a starting point to do the extra work that we needed, and then getting into more of the nitty-gritty details. So this is the research question we started. So this first was getting pitched around late 2016. We had the idea to get started. The problem was we didn't get permission to actually get going until like the summer of 2017. So it's been a little bit. As you can see, the research question that we had was, hey, can we build software that can create and emulate substation protection and SCADA equipment? From the get-go, I was really looking at more of that honeypot side of things. Yeah, it's nice to be able to do virtual devices and have that set up for the communications, but the fun side of things is actually getting them to take a look at, all right, yeah, I have that up there. Now, will any bad guys try to come after it? It would be a lot more fun. Each of those, each of the pieces that we were trying to take a look at there, folks had taken the time to try to work on pieces of that. Some of them had met different levels of success. A bunch of things got abandoned. And so we were going to see what we could do. So first, some definitions. So if you don't already know what a honeypot is, it is basically like a sacrificial computer system that's intended to be the target or attract cyber attacks. Basically, you're baiting a trap for hackers. Generally, when you're trying to talk about the honeypots, you take and rank their interaction. How much interaction can you have with them? We're starting at the low side to high side. That low side of things, we're talking about just that surface area that's out there. It's presenting that, hey, I'm here. I can talk on this protocol. It'll do that initial connection, maybe pass some data, not much beyond that. They can usually be identified really quickly in that they are not maintaining connections. They're not responding with appropriate or realistic data. Whereas on the high side of things, we're talking made up. Sometimes we're talking about them being made up with actual devices. So I have a whole new set of equipment that I am feeding and communicating with. I'm trying to bring in these attackers. I'm trying to watch what they're doing, what exploits they're trying to actually do. We could take and analyze everything they're going after. However, it's really expensive. It's really expensive to try to bring in all that type of equipment. There's another disadvantage is, have I just set up a training tool for somebody that is trying to go after our equipment? Have I just given them a training exercise to play with? So you have to take and balance those things out. Sometimes we have to be very careful with some of the BIOS attacks that are possible. They're rare, but they can easily make a system permanently untrustworthy. Regardless, it also means that the honeypot can be used as a launching point for other attacks if they wind up compromising the system that you do have. And then we're talking about all kinds of legal issues, complications that we got to have to deal with that. So that difficulty trying to purchase all that equipment, the concerns with it being compromised, then having to be replaced if I'm trying to do an entire substation for power, this can get prohibitively costly. So that's what makes trying to take and virtualize these types of devices so much more attractive. So first, I want to talk about some of the previous attempts that were out there. When I was trying to do the initial research on that back in 2016, I was trying to look around, trying to see what kind of honeypot projects were out there, what had been done. One of the first ones, or one of the main ones that I come across, was the HoneyNet project. It's a nonprofit research group that was out there. They've been doing a lot of work and continue to do work around honeypots in general. But there were some things that they did specifically looking at SCADA, but they were more talking about honeypots in general across the internet. So back in 2004, there was this first project, the SCADA HoneyNet, that was done up at the Cisco Critical Infrastructure Assurance Group. They designed a tool that was using one of the applications that the HoneyNet project folks had done up, and it was a C application. They were taking and using that side of it to simulate a really popular PLC. That's a programming logic controller that's sitting out there. It looks to have been abandoned in about 2005. However, if I remember right at the time, I think it still is available up on SourceForge. And then there's a SCADA HoneyNet /SCADA Honeywall that was done by Digital Mon. They started that up in about 2006. Basically, they had two virtual machines, one that was acting like a pass-through for any communications that was going on. They were taking and monitoring the network activity that was going there, highlighting anything that was suspect, and then allowing that interaction to pass through that first VM. The second VM was the actual target that they were using. And there again, they were using that HoneyD to simulate a PLC again. There were ways to take and not have that PLC VM on the backside. They could use that as that pass through and connect to actual devices. Then there was ConPot. ConPot is done up again under that HoneyNet project. It was done in May of 2011, I think is when they started that. It's still being maintained. It was designed to be easy to deploy, modify, and extend. The default configuration for the ConPot was simulating a Siemens PLC. It could be configured as a pass-through to real hardware also. By default, the application included Modbus, HTTP, SNMP, and the S7COM protocols. The last one I would cover here really quick is GasPot. That one was done up in 2015. It was a research tool that they were using. It was using some of those same folks from that HoneyNet. They were bringing things together. They were trying to take and mimic a Guardian AST gas tank monitoring system. It was designed to look like no other existing honeypot, with each instance of it being unique to make fingerprinting by the attackers much more difficult, if not impossible. Eventually, this just got rolled into ConPot. So as I was saying, I started looking at this in 2016, but I had to sell the idea. I had to had to make certain that my bosses knew that I'm not going to fail at this, and we're going to be able to accomplish what we're trying to get at, and that it's not going to be a never-ending project. There had to be an end in sight. I had a limited amount of time to be able to get things done. I was very blessed at the time to have some awesome folks on my team. You heard earlier from Joe Ferguson. He was one of the main gentlemen that was on that, and another was Ryan Thompson. So the first area that I started looking at and how we could take and put these things together, the pieces that I was thinking that we could leverage at the time, it was pretty new. It hadn't been out that long and hadn't made it that big, was using Docker. I was pretty new to Docker, but I thought it was a pretty neat tool. It's an open source tool at the time. I believe now you have to have licenses. It was really active pool of developers. It's constantly going. So they've done really well with that. The gist of it is it was set up so you can automate deployment of applications inside of a software container. So rather than taking up so much room as the virtual machines that we were used to, these are much smaller, compact. You could limit what it was doing, what connections it had to the outside world, things like that. Made things a lot less overhead for each of the instances that you're trying to spin up. So the second tool that I was going to take a look at was that Honeypot. So since Honeypot had already been out there, it already had several of the protocols that we want to take a look at for the virtualization that we were trying to do. And it had already been going for a few years. It had active developers working on it. The only limitation, I think, at the time, the version that we were on was written in Python 2.7. Everybody had an idea of when Python 3 was, or when 7 was going to, or I'm sorry, when 2 was going to be rolling out, and Python 3 was going to be going. But a lot of the libraries that we were trying to use for these different protocols, not everything had been ported over to Python 3 yet. Everything was still in 2. So that's where we were working with. And again, the reason why we're trying to take a look at that Docker is that's that ability to take and scale. We could do multiple instances and do several of them. Some of the communications pieces that were out there. Here again, we're trying to take and center this around that Docker tool. Within it, it has that ability to set up Mac VLANs, so the Mac virtual LANs. Some of the applications that are out there, when they're monitoring network traffic, they expect to be able to directly connect to a physical network. In this type of situation, you can use a Mac VLAN network driver to assign a MAC address to each of the container's virtual network interfaces, making it appear as a physical network on the net and directly connected to a physical network. Also, Docker took care of manipulating the IP tables that we needed that gave us those rules to take and provide network isolation and be able to keep each of the individual containers separate. So the last area was this, of the infrastructure we were talking at was the coordination. This is the piece of the puzzle that take and bring three items together. They can take and move that honeypot that we were working on from a low interaction to a higher interaction. The responsiveness is the idea of the software being able to respond and provide realistic data of a specific scenario. The interaction of the relays allows devices that are related to respond appropriately to changes in one another. And lastly, the oversight piece being the ability to maintain monitoring of the communications that are happening across the system. So that was that general plan. That was the idea of what we could bring together. So we started off in baby steps. That first thing was, okay, can we take and virtualize a single device? Can we make certain that we have a good footprint for a public and segregated private network? One of the protocols that were being developed on this is HTTP. The relay that we were taking a look at first trying to emulate was the SEL 351. It has a web server that's on there. It's a read-only web server. You can't make any changes from it, but you can view and monitor the settings that are sitting there on that device. Also, a big thing for a lot of the SCL devices is a telnet protocol. This here gives an HMI that you can use over telnet. This can give you different levels of security that you're logging in, what kind of changes that you can make. Do I have my basic login? Do I have the next level up for the engineers? Do I have the engineers that are actually commissioning the devices? Each one of those have different permissions that they have on there. Our initial attempt was, hey, can we get telnet going? Can we get basic login functionality? And at the same time, with all of these things here, we needed to have good logging. We want to be able to track what the heck was going on, who was talking, when it was talking, who was talking to what. Also, as been discussed a few times here, one of the big tools that are out there, it's nice to be able to see the traffic that's actually going across there. And so we were used to using Wireshark a lot when we were trying to see what traffic was being sent, how it was being sent, what values are being sent, and how they were being used. If you have ever used Wireshark, it has the ability to take and do like it can do packet capturing. The idea is that is I'm recording the network traffic that is coming into a specific point, and I can take and either play that back or step through all of the communications that have come across that. There's one more piece that we did here in development, and I'll leave that obscured for now, and we'll talk about that at the end. So stage 2, we were going in there and really fleshing out that telnet HMI, working with the FTP protocol. This is the ability to take and load settings files or download settings files. There was a Modbus protocol. Like I said, Docker, I'm sorry, not Docker, but Honeypot already came with a little bit of a Modbus protocol developed. We had to do a lot more work, and we had to set that up in a way so that when we were done, we weren't just hard coding in how to do an SEL 351. We had a templated way to go through and implement any other of the SEL devices that we wanted to go put that effort into. And then we were getting our initial DMP3 protocol up and running. Later on, we were taking some more efforts with those PCaps, doing the automation and how we were recording those, how we were maintaining that information. If you've ever done the packet capturing, if you have a lot of traffic in there, those files can get really big, really quick. And so we were trying to find ways to cut down on that. One of the things that the SEL devices also have with some of those control devices, they have redundant ports on them. So you'll have like 2 LAN ports or 2 fiber, or it can have a mixture of 2. We were looking there for a little while at, do we need to worry about doing these redundant ports? It's a piece that you can do to improve that fail-safe. Hey, I can't get to it from this point. I can get to it at another point. And I believe we have it in there, but it just wasn't stressed later on in the project. And since Schweitzer, our power company, we have a bunch of power engineers that are here on the same floor. We had been working with them, and since they wanted to be able to use the tool, they had asked us to make sure we fleshed out a good power model behind the scenes so that it would at least give some realistic data, some semblance of realism as that information is in there. And we wanted to have a good way to make that look good. Again, we were taking more steps in there for the automation steps, the setting that thing up, configuring it, changing it from this relay to a different relay from a different type. Eventually, we wound up doing 2 SEL relays. In the end, we did a 351 and 751. Later, we were trying to get into some more of those historic values. What we're talking about there is on DMP3. You can request events. So somebody has gone through and tripped a breaker. There should be a history of the information around that. It's it generates an event report. We wanted to be able to, if I go in to DMP3 and request that event reports, I will actually be seeing those things. They would match up with what I saw in the power model. We're trying to get some of that realism. Again, we went back and touched on one of those things that I'll leave toward the end. On the last stage, we were trying to work out a bunch of different scenarios of how the relays could be configured, set up, how that matched up with the power model, the communications structure. We did that effort to get that 751 emulation up also. And then maturing out the logging, the alerts, the PCAPs, everything that we were doing there. So the main pieces, so Honeypot is that main process that's being run. That's we were running inside the Docker there. Within it, we had several sub-processes going, reaching out to a command line tool, things like that. Unfortunately, we did the no-no and we added greenlets also. Why did we do that? Why did we torture ourselves? Well, Honeypot was originally written with greenlets in mind. But as we were getting into dealing with a lot of the file system management and the FTP, the packet capturing, all of that, we needed the ability to have those in processes rather than the greenlets. If you don't know what greenlets are, you can think of them about threading. And if you look it up, you'll see that it's not a good idea to mix processes and threading. So it was a nightmare. But there was good reasons why we went to it. We were also trying to make certain that we actually got things completed in a certain time, and there were certain protocols that were already done, and we had already gotten started down a route. So, all right, we're going to grin and bear it, and we're going to get it done. So those sub-processes, there was 4 main sub-processes. One was a file system management. That was what was taking a look at handling all the logging. That's what was taking a look at all the packet capturing. It was managing how files were named, where they were stored, what was going on there. Then we had a command line tool that we were launching off from within the application. That was T-Shark. That is a basically that is Wireshark without a GUI, and it just gives us that ability to take and capture all the traffic that was going across there. Again, as I said, the FTP protocol, we had to have that in process because it was actually reaching out to a specific folder that we had files setting in that gave them that ability to take and download those files across that protocol. It just became a problem if we did not have that in processes because of the difficulty of taking and downloading the file, the time that took, if having those over there with the threads, you wound up starving out all the rest of the threads because the FTP was just hogging up all the resources. And the last thing there, again, I'm obscuring this here towards the end, and we'll cover that last sub-process there. The greenlets that we were looking at, this is where we're taking a look at all the different protocols that we needed to implement. So ICMP, so basically ping, Telnet, HTTP, Modbus, and DNP3. So I want to make sure that I give credit where credit is due. So the libraries that we were taking a look at, first we started off with Honeypot. That's being run by Mushmush. That is the way it's spelled. If you go out to the GitHub and you look up for Honeypot on Mushmush, that's what you'll find out there. The file system management, that was something that we handled. That was a mixture of a lot of work that we did. This is kind of what Honeypot had in place. This is what we need to handle for T-Shark. This is what we need to handle for FTP. So we took and merged everything that we needed into that process there. Again, T-Shark is a command line version of Wireshark. FTP, there was a open source library that was out on GitHub. There was a version of a library that was kind of worked on. I don't believe it's being maintained any longer, but it at least gave us an idea of here's how we can implement that protocol. That's the library we started from, and then we heavily modified it. There's another library I'll go in at the end. Again, ICMP, there was a there was a ping library that was out there. I believe that was done up in like 2009. I don't think anybody's touched it since then, but it works great. We had to do some edits there, not a ton on that one. The HTTP lib, that's part of the Python libraries that was there. Modbus, we started with Modbus TK. We had to do a lot of editing. That was originally what the library that Honeypot had started with, and we did some edits to make that happen there. DMP3 was a bear. There was this DMP simple that had been out there that gave us that starting, but you had to generate every byte that you wanted for a package and send that. There was the protocol was not fleshed out. It was just here's how to handle traffic going across on DMP3, not necessarily being able to take and parse out the protocol as you were going through there. And the same thing on the telnet. There was an example of how to do up a telnet HMI, and then we get into that. So I wanted to go back to a couple of the protocols that were talked about earlier. So we were talking about Modbus previously, and one of the difficulties with Modbus, yes, you have a limited amount of functions that are there. Yes, you have, hey, I can only send binary, or I can only send a uint16. Well, the protocol is defined that way, but the developers of the equipment that is actually using that, they can do whatever they want around those bounds. So what if I am wanting to send a complex value? So I have my real portion of the value. I have my imaginary portion of the value. How do I send that in a uint16? Well, I can take and break that up. I can have one register that is the real values for it and another register that is the complex. And as long as my device knows, my data sheet knows, and those that are trying to ping me for that information on Modbus know that, oh, hey, that uint16 that came across there, yes, you asked for two of them. They're at these addresses, and this is what they actually equal. In that same way, you can wind up doing 32-bit values, or however you want to do it. I can have several registers that could be part of a value that I'm trying to send across there. So rather than limiting myself to only uint16 values, I can use that as just 16 bits and then use several registers to be able to flush out a larger data values that I'm trying to send across there. And so that was some of the nightmare that we put ourselves through to try to get that thing set up to be able to play with that. It was the same idea with the DMP3. Modbus and DMP3, they have two different things. Within the relays themselves, you had about 8,000 different values that are on the relays themselves. There is a subset that the device allows to communicate over Modbus. And then you have a programmable subset of those that are allowable that I have actually said these values are sitting at these registers or these addresses in Modbus. It's the same idea on DMP3. DMP3 has a subset of all the values that are possible on the relay. Here's the values that DMP3 will allow. Oh, also on DMP3, yes, I can look at these values, but only this subset of those are even writable, and so on. Then as I said, mentioned it briefly earlier, Telnet, the HMI was an absolute nightmare. So getting into some of those nitty gritty details, this was the general idea of what we were trying to do with the network footprint. We had an idea on the left side there of, hey, here's the computers that we have in the lab. Each of us can have up our own session or Docker running. Inside that, we can have a Honeypot running inside that. We have a switch that's sitting out there. We have an actual RTAC or the RTU, as David had mentioned earlier. We had two actual SAL devices that were sitting out there, and we were running values across those. it just gave us a way to take and compare from my Docker to Joe's Docker to the actual device and see the differences in the communications that were going on there. Different ways of trying to, on the right-hand side, were different ways of trying to launch off multiple instances, that ability to take and store, have all of them storing in a central location. That's the idea of the first one. Then we get into the logging. So Honeypot had an idea already in place for logging, and we just expanded on that. We needed to find a way to take an alert on different kind of messages. We didn't want to alert on every line going through, but there were specific things that we definitely wanted to connect to. That initial connection for an FTP or for a telnet, the password attempts on a telnet, those kind of things. And each of the protocols that we had set up, each of those processes and agreements, they each had their own logging levels that we could take and adapt to. Originally, we had not done that. That became unbearable to deal with as we were trying to troubleshoot. Hey, I'm done with this protocol. Let's work on the next protocol. Oh crap, my logs are completely full of the protocol that I'm already done with, and now I need to see what's going on with the problems that I'm having with the current one that I'm on. So we had to find a way to take and filter those for each of the processes that we were doing. So one of the things I was talking about earlier with that T-Shark, we were capturing the traffic that was coming across on the devices. So the idea that we had worked out was, hey, we're constantly recording. We're constantly recording a PCap file. So if you look at the graphic that you have here, that upper left, you have the 0, 1, 2, 3, 4. So we had five PCap files that were sitting in a rotating buffer. So if I turned on the application and at the end of the day I shut it down, at a minimum, I'd always have at least those last 5 packet captures that were there. So if for some reason, somehow, somebody was able to bring our Honeypot down, we'd have that a PCap of that last bit of traffic that we set in there. And then after that rolling window that we set up there, what we did is, if we had a specific alert that we had found, we made certain that we flagged that PCap file and one before and after it in the timeline. So as you can see in that graphic, you've got a couple of these dark blue ones. If an alert happened on one of the protocols during that time frame, we would get the dark blue and the light blue PCAPs around it. Any of those that did not have any alerts or nothing interesting, we deleted those PCAPs as we were going, because it just wound up becoming too much trying to hang on to all of that traffic. We did configure this, or we did template this out, so we could take and expand that that window that we had, that 5 window rolling that we were doing there. It could make more sense to only have 3 windows. Depending on how I set up each of those windows, was I breaking every 1 minute, every 30 seconds, every 5 minutes, however we wanted to do that. And so we did leave that open up and try to keep that configurable. As I said, we were doing a lot of templates to try to do everything behind the scenes. We wanted the code not to be hard-coded. We did not want settings for a specific device to be hard-coded in the protocols that we were doing, any of the libraries that we're doing. We're trying to bring those in as these templates on startup so that it knew how to take and configure itself. So Honeypot was originally starts off, it has a databus. Basically think of it as a database that's handling all the different variables that you're trying to track. And as we went along in each of the different protocols and later, okay, here's an internal variable to the relay that we have. This is how I format it if I want to see it in text. This is how I format it if I'm wanting to send it. This is how I scale it. Oh, hey, this is a variable that I need to, at the time that somebody asks for it, look it up. So that first entry that we have there. That's the N megawatt hour amps, I believe. And so that was a floating point number. It would be 8 digits with two digits beyond the decimal point. It needed to be looked up for in our power table to look up at a specific time. Hey, what was the value at that time? And if there were some scalars that we needed to take and apply to that. Also, there were other variables that could be entered from the HMI. And so whoever wrote the HMI, we were having nightmares from them on certain things because they would have a specific value that sometimes it's a Boolean on-off value, and sometimes it's a float. And so we needed to have ways to take and filter that out. What type is it? What are the parameters? Is it possible to be just off? What are the ranges? What's the precision that it can be? And so on. Then if I were trying to request that value in the HMI, what was the prompt to be able to get that value? And then what was the default value that it was set to? Or did I have a specific entry in the databus that already had that value, and I'm going to take a reference to that value instead? Again, continuing on with templates, this is where we took and really got into the HMI, being able to, if I typed in a MET command in Telnet, that's the meter. And then if I had the option E, so MET space E, that would pull up this format, and then it would know that, oh, in each of these variables in here, this is the value I need to go look up to fill out that output to the HMI. Here again, we kind of went overboard on this one a little. We wanted to have a really good idea of getting some variables for the power, what that looked like. We spent a lot of time here, probably too much time, honestly, but trying to get an idea of what does the power generally look like. Okay, now I have this pattern that I'm looking at. Let's add some variation in there. I need to take and either lower or increase those spikes, move those spikes left or right. So this is an image of what the power generally looks like throughout the day. So starting off at midnight, it's pretty low till around 6 a.m. Then it starts to spike around 10 a.m., comes back down a little around lunch, stays pretty steady throughout the day. End of the day, it really peaks out till we're kind of done for the evening, and then drops back out. That was the gist of it. Then we take and add noise to it, and each day that the application was up and running, it would regenerate one of these models. And so it did not have to do all the math on the fly. It was only done at the end of the day. We took a lot of time driving out different scenarios that we could set up. What were the values that we needed to be concerned with to drive that power model? And then on the right-hand side here, if I had several of the devices up and running, I need them to be aware of one another, where they're at in that power model, and understand how to react to that power model. So I can show this example now. So as I was talking about, they need to be taken and be interconnected. So this is a larger substation coming down to 2 substations, then coming down to like more of a neighborhood. This is just an idea. I'm not a power engineer. This is just the idea to give you what's going on there. So if I wanted to cut out that line, if in our scenario, somebody goes in and pops that breaker, there are portions of the power model that need to be aware that, oh, hey, that line is off now. So that line now has shut off. There's no power running through those lines. Those devices that were upstream of that need to be affected because there's nobody drawing that power through them any longer, and so on. If I cut this one, then all of those downstream needed to be aware that, hey, somebody upstream of me got cut. So I don't have any power, so I need to go to 0 now. So that was the idea of those scenarios. So this is where I ask, I guess, my first question to everybody else. Can anybody tell me what it is that I have been not showing so far? What is a key thing that I care about with the Honeypot? All right, I'm just going to give a few more seconds. Well, one of the things I care about is, can anybody tell if it's a honeypot? I need to have a way to obscure it. I need to not have an easy way to identify that I'm talking to a computer, or I need them to believe that they're actually talking to a substation or to one of the relays that we have there. That's why it matters. What are some of those tools that are out there that we got to be concerned with? Well, there's NMAP. If I can just use the NMAP and fingerprint the device or that IP that I'm going to, then it can readily tell me, oh, wait, hey, you're talking to a Windows machine, or you're talking to Ubuntu. It can identify those things. Or if I remember right, it can also show that OS, but it can also tell you what is the type of, who is the manufacturer of the network interface card that is sitting there. Because you have specific MAC addresses that are assigned in there. There's different ways that each of them take and respond to the different protocols. So you have different ways that NMAP can take and do that fingerprinting. So that's why we're concerned with that. So one of the libraries that I didn't cover earlier was this OS Chameleon. It was also done by the same folks that did Honeypot, that mush. They had a neat way to take a look at, okay, these are the ways that NMAP can take and fingerprint the device that they're trying to reach. If I watch for that traffic, can I respond back with the responses that NMAP is expecting for the actual device, rather than what it's actually talking to with the Honeypot? Oh, and the last question that I have there is, okay, how did it stand up to scrutiny? How did things work out there? So with that NMAP, if I did that full scan on the NMAP, whether I was going after specific ports or I'm trying to look at the operating system, you had your command line entry, and then NMAP will send several different messages that it's going to the device. It then sees how the device responds, and then based on those characteristics, how fast it does that, how it responds, what order it responds, that's how it can take and identify what this fingerprint looks like. So what it will do a lot of times is it's going to send a malformed traffic to a device, but it won't be a single one thing that's malformed. It'll send a few things that are malformed. So it's the wrong size, it's the wrong type, it's the wrong data, or invalid type of data. How does the device respond? Which of those malformed pieces? I sent one item that has all three of these things messed up on it. How does it take and respond? Oh, it responded to this first. Okay, sweet. Now let me try this other malformed. Which one did it respond to first? And that's how we can take and go through and take an fingerprint what it's talking to. And we had reached a point there with all the protocols at that time, and had been able to completely obfuscate from the NMAP scans. We were perfectly matching the equivalent scans of an actual device, both the 351 and the 751. You can completely hide the Ubuntu OS that was running behind the scenes there. And the NMAP was coming up with a complete match. Now, if you take a look at it, the fingerprint that it shows here doesn't say an SCL351. Oh, excuse me. It shows an HP LaserJet. And for some reason, the HP LaserJet and that SCL351 wound up having the same fingerprint. And so that's what made it into the database for NMAP. An internet version of that NMAP scanning is Shodan. So Shodan has a way that they're constantly looking out there and seeing, oh, hey, look, this IP is this kind of device, and oh, look, it's got the default password on it. There's a lot of that kind of information that you can find out there on Shodan. Well, one of the tools that they have there is this, hey, is it a honeypot or not? And we were able to plug in our IP to it and get it to pop up thinking that it's the real system. I remember going through one of the papers and discussions that I had gone through originally in 2016. And one of the complaints by the folks there at Mush was that as folks were using the Honeypot application, rather than taking the time to do the edits that they suggested, they were just running it. People were putting that out there as the default. And so Shodan would show 50 different instances of Honeypot up and running with the default settings. And it immediately had identified, oh, hey, look, that's Honeypot. We've already seen it. I know what that fingerprint looks like. One of the difficulties that we did run into with Shodan, though, the first time we tried to set this up, we had, rather than having a physical device and having that device set to one of the public IPs here at the company, we had set this up in the cloud, tried to set it up that way. Went to Shodan, told, hey, Shodan, could you go scan this IP? And without it sending any traffic to that IP, Shodan was able to say, nope, it's a honeypot. We cannot confirm for certain, but basically the only thing that we could think of was that maybe that IP, the IP blocks that it was taking a look at, it already knew those to be out on the cloud and immediately marked those as a honeypot. Later on, once we had an actual device and had a specific IP to connect to one of the public-facing IPs that SEL had, we were able to fool it that way. So how did it perform out in the wild? So as I said, we had a few different ways of testing that. We had tried it on the cloud. We had played with that for a little bit, had seen some efforts that were out there on that, but the better traffic that we were seeing was when we had that public IP. And a funny story with that really quickly was I remember having the IT folks here with me as we were trying to take and configure everything, trying to get through all the firewalls that we needed to here to be able to connect to the device that we had hooked up in our lab. And one of the gentlemen was sitting here beside me as he was making those edits, and he had just hit enter, and I immediately started seeing traffic. And it was within seconds of him hitting enter, I was getting unsolicited traffic on that IP. And it was just kind of shocking. I have kind of likened that now. When I think of my mailbox at home, I know most of the time the junk that I have out there in my mailbox at home, half of that is spam, not spam, but advertisements junk. It's the same idea for my regular email. Most of the time what I'm getting is a bunch of junk mail that's out there. Well, a lot of the traffic that's sitting out there on the internet, it's the same way. A lot of it is just garbage that is coming, and there's all these constant sweeps that are going. How much of that is malicious, I don't know, but I do know there's a lot of it. So the first chance we had out there to do this testing, they allowed us to keep it up for about a week. I had to make certain that I was staying with it, monitoring it at all times, watching traffic, passing any problems up to our IT folks, because they were concerned with, as I said in the beginning, being able to take and pivot from there into the rest of the company. So we're trying to make certain that that's not happening at all. As we were going through that, we were able to take and document over 200 different probing attempts during that week. And these were, a lot of these different IPs were repeated attempts. and this is just in a single week, it did not seem like any of these were somebody behind the keyboard and attacking. These all looked like automated sweeps that were going on. The second time that we went at it, though, we had kind of figured out that, hey, wait a second, we're accidentally filtering a lot of the traffic that we have here. And so we took an effort to not just watch for any of the SCADA protocols, but also alert on any other ports that these scans may be hitting. So we'd have an IP that would come in and hit multiple ports on the device. Well, we wanted to see what are the other ports that they're hitting at the same time. So that second time through, we got a lot more hits, of course, because we're looking at more ports. We logged over 1,200 different IPs, and each of those were trying over 1,600 different ports. A lot of traffic were on some of the SCADA protocols. We saw tailnet attempts. We saw FTP attempts. We'd see a lot of that kind of probing of, hey, how does this respond when I send this malformed type of information? So we're getting some cool research. We're having a lot of fun with it. And then security came down and said, no. I didn't realize it. And somebody up higher had finally come down and said, wait a second, you have a public IP and you're doing what with it? There are periodic evaluations that wind up happening for a lot of the companies that are out there. Hey, how good is your cybersecurity stance? And those evaluations, if that IP is sitting there open and, oh, look, there's this neat tool that I can access and it's open to this port and that port. Yeah, so security came down and said, nope, you got to turn it off. So last thing to cover here is, okay, is this tool available? Well, yes and no. No, we don't have that pushed out to everybody to be able to use. Sometimes we can use it here in our testing environment. But as I said, security does not want on a public IP, so we haven't been able to use it in that fashion. However, when we were asked to assist in supporting this effort this weekend, we had some concerns with, here, let's send a bunch of devices for the Hack the Power effort and their capture the flag. And so this was a better idea that we could take and spin up this honeypot that we have out there that is emulating these devices. And this winds up being one of the targets that you have during the CTF. The last thing that I want to cover here really quickly was some misconceptions. So, and I think this is one of the reasons that why the company had asked us to go more with honeypot rather than actual devices. So when you're looking at all these different protocols, as has been stated earlier, some of them have security, some do not. If I am telling a device to do something that is programmed into the protocol and is programmed onto the device is doing what it's told to do. The device wasn't hacked. The security was hacked that gave you access to that network and or access to that device. So I think that was where most of the concerns was, oh, hey, we put one of our actual devices there and, oh, look, it's been hacked. And that was, I believe, was more of our concern there. It was, no. We have a device here. We're taking advantage of holes that we've purposely put in place to be able to hack into the system. And so rather than actually hacking into a device, we've actually hacked into that network that's there. So I think that basically covers everything that I wanted to cover. Are there any questions? Yes, there is. It's this honeypot is going to be in the CTF. Exactly where and how, that's up to you guys to find out, not me.